Okay, so hi, I'm Wen-Jie from National Jiao Tong University, Taiwan, and I'm glad to be here to present FaceWidgets, exploring tangible interaction on face with head-mounted displays. And this work was in collaboration with Yang and Liwei from NCTU. So, okay. So, FaceWidgets is a control interface integrated on the HMD backside, and which allows the user to to manipulate the controls directly. And let me introduce our motivation. As we know, freehand input has been a popular technique for the head-mount displays. However, when the interaction in time increases, it will become, users may feel fatigue. And FaceTouch allows the user interface on the HMD backside, and it provides touch interactions, and we believe the touch interactions can be combined with the mid-air finger input in the future interactions. However, besides touch interactions, we believe there's still some the design space on the HMD backside has yet been explored. What if we want to interact with the physical objects at this interaction space? So we install the physical controls on the HMD backside, and on the HMD backside, which allows the user to manipulate these controls directly with his hand. And we do this because we want to enhance the HMD input without hand controllers and assess the physical controls when you interact with the virtual one. So this work introduced how we learn to enable direct manipulation with FaceWidgets. So here is an application of FaceWidgets. You can see the user can manipulate these controls directly with his hand in VR. So our main principle is about direct manipulation. We collocate the virtual control and the physical control on the HMD backside. However, if you put the controls too close to the backside, it will make the user feel eye strain. It's difficult for eye converge. And we extend the control to a distance from the HMD backside, which resolves this eye convergence problem. And we can maintain the collocation and for direct manipulation. So it turns out to be a lift in our final prototype. We can use a lift to extend control from the HMD backside and complete this interaction. And now let's look into an example of FaceWidgets. For example, the user is going to turn on the light at this in the VR. So first of all, he will fixate his viewpoint on the light. However, the button over here is within the disparity of the light and the user's eye. So it will cause the double vision. And when double vision occurs, the user might be confused about which control should he use. So to address this problem, we use a rich canvas, which is our interaction design, and to reduce this disparity at the same depth to the controls. So when the user he fixates at the rich canvas, double vision will be eliminated, and the user can successfully complete the task. And after interaction ends, the rich canvas will fade out. So let me see another video about our interactions. The user used the rich canvas to reduce the double vision. And here you can see the rich canvas, and the user can use direct manipulation on these physical buttons. So let me show you about our implementation. So our main purpose is direct manipulation, and we have to extend the virtual buttons to a distance from the HMD backside. So this is our prototype, FaceWidgets, and you can see the physical controls are mounted on the control panel. And we have a lift driven by stepper motors, which can extend the control. And the reflective markers are for external tracking. So here, the leaf can extend these controls and to align with the virtual counterparts. And also, we use the leaf because it is foldable and can reduce the obstruction and be more portable when not in use. So here is about our design about control panel. And you can see we can plug in the control panel to the headers on FaceWidgets. And also, to identify which control panel it is, we use the magnets on the control panel backside and use Hall sensor to detect which one it is. So this is how we can do. We can reconfigure the control panel and change the applications. And since the Oculus CV1 doesn't have the tracking ability on hands, so we use VR gloves to provide external tracking on user's hand. And for the OptiTrack, because our prototype blocks the tracking of the Oculus HMD, so we use OptiTrack to restore the tracking. And all the track objects are calibrated by calculating their Euclidean transformation, so that all the track object is under the same coordination. So now I will show our interaction design. And just as I mentioned, because double vision will occur in our interaction, so we use a rich canvas to reduce the disparity so that user can manipulate our physical controls. So this video shows the VR scene of the rich canvas, and we blur and black the peripheral region, and the fade in and fade out is controlled by the user's palm. So this is the second interaction technique called palm facing gesture, and a user can use the palm facing gesture to invoke the rich canvas. And now I will show some example use cases about our prototype. So we designed two layouts about the control panel. The first one is fixed layout, and the second one is contextual input, and each of them related to one application. So in fixed layout, each control is maps to one single function. So we refer this application to the firmware and create a 360 video player. So at first place, the user turns on the little planet switch, and he can get an overview of the environment. And he can label the content inside the VR. And also we provide a viewport knob, which allows the user to turn his viewport to another direction. And he can use the reorientation button to redirect back to the label content. And what if there are multiple things to manage in one application? So we create contextual input. So it's a small set of physical controls on the backside, and which allows you to control different objects. So here, for example, the user turns on the light at first place. And then he uses the same button to start the music player. Okay. And he moves on to the next one. So in this application, the single control has maps to different multiple functions depending on which one the user is interacting with. And now we conducted 3 user studies to inform our design of prototype. And we conduct 3. The first one is the operation distance. So here we have to extend the controls at the distance from the HMD backside. But at which distance? So here we study the minima depth that user can still perceive the virtual controls comfortably, and the user has to adjust the depth of the cylinder from 33 locations, which are evenly distributed on the HMD backside. So here's the task. The user adjusts a cylinder at the HMD backside to the distance that he feels comfortable and can see the controls clearly. Okay. And this is the other initial position in our task. So let's see the results. The overall average of these 33 positions was about 12 centimeters, and the center region is more flatter than the both sides. So we decide to, the blue surface shows the interpolation of our results. And we added 2 standard deviations at the center to 20 centimeters as our operation distance. And we chose 12 positions evenly over this region to place physical controls. So in study 1, we decided to extend the controls to 20 centimeters from the user's eye position. And now we're interested in whether showing hands can facilitate our interactions. So we conduct the second user study. There's an independent variable interface with show hand and no hand. And the user has to rotate and press a knob randomized from 12 positions in our task. And we build a prototype which fixed at 20 centimeters with 12 knobs. And we use knobs to resemble the typical tangible interactions. So our setup can reduce a part of the weight caused by our prototype. And we use OptiTrack to track the user's fingertips and their head, and the headset. So here's the task. In the show hand condition, the user can manipulate these controls with his fingertips. In the no hand condition, the user can only rely on his proprioception. So in this study, we measure the completion time and the error rate and offset distance. And for each condition, we measure the oculomotor or simulated sickness questionnaire and a subset of NASA TOX. And here are the results. And we found out that displaying hand can significantly reduce the error rate and offset error. And it can also reduce the mental and physical demand. So although using proprioception, the user can operate FaceWidgets, but using hand reference can make the interaction more precise and effortless. So we decided to add the hand reference in our final prototype. However, which type of the hand model should we present? So we conduct an exploratory study to investigate the preference on hand models and gathering some subjective feedback. Okay, so we provide 4 hand models, and the user have to experience 4 hand models among 2 applications, which are fingertips and transparent, silhouette, and realistic hand. And we also asked the participants to rate on these 4 usability questions. And for more details, please refer to our paper. And so in these 4 dimensions, the user, we receive some positive feedback, and the user can operate the FaceWidgets as well. And on the preference, the users are most like the transparent one among the first and the second place. So the fingertips can provide precise control, but it lacks of the sense of presence. Realistic hand has the highest sense of presence, but cause some occlusion. And the silhouette hand and transparent can allow presence of hand and without occlusion. So we chose the transparent hand as in our final prototype. And for the user feedback, they think our interaction design are intuitive and easy to use. And one participant said that the which canvas draws back from the 3D environment. So we think this can be studied in the future study to improve the transition and usability. So in the last study, we decided to choose to display transparent hand. And now I will wrap it up. So there's still some parts to improve. And the total weight, we want to replace the stepper motors with lighter actuators and to reduce the weight. And also, we want to replace the parts of FaceWidgets into lightweight materials like cardboard. And we use external tracking of the hand, and we hope in the future the inside-out tracking can replace this, can provide hand tracking, and so that we can enable our interactions. And another improvement is on the number of the controls, because now the numbers of controls are limited, and we hope to use haptic retargeting to repurpose the virtual controls into a small set of physical ones, so that we can increase the control. So now I will present our contribution of this work and conclude my presentation. We have presented FaceWidgets and HMD that integrates physical control on the HMD backside, which allows the direct manipulation in VR. And we provide 2 interaction techniques, which canvas and palm facing gesture, which can enhance the direct manipulation on the HMD backside. And finally, we conducted 3 user studies to suggest the design space at this interaction space. So thank you for your attention, and I'm happy to answer your questions.
Great, thank you, Wen-Jie. Any questions? I have one to get started. The examples that you showed were all single-user applications. Does this have any implications for multi-user interaction?
Yes, it is possible. But all we have to do is using some AR techniques to visualize what exactly the function of the physical controls and what the user is doing inside the interaction, so that the non-VR user can join the interaction of the VR user. Yes.
Any other questions in the audience? We have time for a few. I have another question I could ask.
Okay.
Did you consider using, instead of having the lifting mechanism, using like a redirection, so a virtual hand that doesn't match the position of the physical hand?
Like
the virtual UI could be farther ahead
okay.
while your physical hand is actually here.
Yeah, but I think in this context, there will be some mismatch between the physical objects and the virtual objects. So we decide to enable direct manipulation, so that what you see is what you can touch. That's our main purpose in this work. Yeah.
Okay, well, if there's no further questions, we'll thank the speaker again.
Thank you.